So welcome to part 2 in our tutorials on remote sensing. So in this video we're going to talk briefly about additive RGB color, and then we're going to review the relationship between spectral bands and RGB color. So we left off talking about spectral signatures and spectral resolution. So just to recap quickly, this is an example of a spectral signature for, in this case, grass. And there are 4 spectral bands here. Bands 1 through 3 are in the visible light spectrum, and then band 4 is in the near infrared. So when we're dealing with remote sensing, we're usually dealing with raster data. So here's a golf course, and I think I see a swimming pool from above. And here's part of the swimming pool and the edge of the golf course when we zoom in. And you can see that this red box represents roughly the area that we zoomed in on. And when we zoom in, we can see that the entire image is composed of raster cells. So since we're dealing with raster cells, what do you think grass would look like in a raster cell? That is, what color do you think grass would be displayed as? Well, it turns out that computer monitors can really only display in 3 colors: red, green, and blue. And you can see that by combining or adding together these colors, you can get other colors like yellow, magenta, and this cyan color. So in this case, we're dealing with what we call additive color, since we're combining together these 3 colors, red, green, and blue, or RGB, to make other colors. So back to the question of what a raster cell representing a grassy place, like let's say Battelle Beach, would look like. Well, if we're just dealing with our 3 bands in the visible spectrum, this is a pretty easy question to answer. We have 3 bands and 3 display colors to assign. So we can assign the display color blue to band 1, the display color green to band 2, and the display color red to band 3. So in this case, a raster cell full of grass would probably end up looking a pretty familiar green color. Because the reflectance value is highest for band 2, and because we assign the display color green to represent this band, a raster cell full of grass ends up looking green. So in this case, in the spectrum of visible light, since we're assigning the display color blue to things we normally see as blue, green to things we normally see as green, and red to things we normally see as red, we're essentially asking the computer to display things the way we usually see them. So here's an example of what an image might look like. And here's our golf course again in Phoenix, Arizona. And you can see grass is appearing as green, the swimming pool is appearing as blue, and soil is appearing pretty soil colored. And this is what we call a true color image. But what if we switch these so that band 1 was represented by the color green and band 2 was represented by the color blue? So in this case, what color do you think grass would be? Well, it makes sense that it would be blue, since band 2, the band with the highest reflectance values, is now represented by the color blue. If we go back to our golf course, we can see that grass is now represented by a dark blue. And this is what we call a false color image, since we're displaying things in colors that we're not accustomed to seeing. But what if we wanted to display a band in a region outside of visible light? Let's say a band in the near infrared region. So we'll take away band 1, since the image that we'll be working with doesn't have a band in the blue region, but has 1 band in the green region, 1 in the red region, and 1 in the near infrared. So in the case of band 4, we're dealing with a band in a region with wavelengths that we can't see. So obviously we can't ask the computer to display values in the near infrared region with a near infrared color. So instead we're going to have to arbitrarily assign one of our colors, red, green, or blue, to represent values in this band. So let's say that we assign the display color of green to band 2, the display color of red to band 3, and the display color of blue to band 4, the band in the near infrared region. So in this case, what color do you think a raster cell full of grass would be? Well, I'm thinking it would be blue, since the strongest reflectance values for grass are in the band represented by the color blue. So here's what that might look like. So the golf course is now being displayed in this intense blue color because the extremely high values in band 4, the band in the near infrared region, are represented by the color blue. And you can just make out the swimming pool that looks like it is now being displayed as green. And if we enlarge the image, we can see that the swimming pool is definitely being displayed as green. So in this case, what color do you think the swimming pool would be if we switched these so that band 2 values were displayed as red and band 3 values were displayed as green? And here's your answer. So you can see that the swimming pool is now displayed as red. And with this band combination, you can actually start to see that it looks like there might be a hole in the middle of the swimming pool. You can see that when we zoom in, there's definitely a hole there, so it strikes me as odd, and I'm beginning to wonder if it's even a swimming pool. But when we zoom in with Google Earth, we can see it is a swimming pool after all, just a strangely shaped one. And we'll go back to our 4 different images of Phoenix, Arizona. We have 1 true color image and 3 false color images. And you can see that depending on the way that we've displayed our different bands, it's easier to distinguish certain things on the ground. So in these bottom 2 images, you can see that the golf course pops out a lot more. Whereas in these upper images, it might be able to make out houses and things, since the golf course isn't so overwhelming. So you can see that it's pretty easy to change the way an image is displayed without actually changing the reflectance values of the data. And that's the main point of this lesson, and that about sums it up for today. So thanks for listening.